Well, all right. Thank you everyone for joining us today. This is the Collegiate Wind Competition Design Team's final design review. Our team members are Brighton Boomel, myself, Garrett Compton, Donovan Crow, Anders Dahl, Thomas Ford, Nadia Morris, and Jacob St. Marie. And our sponsor is Dr. Michael Stollinger. Just to give you an overview of our presentation today, we're going to start off by talking about a project overview, then go into the initial design, then our detailed site design, our financial modeling, our design results, our design validation, and our conclusions. I'm going to start us off by talking about the project summary. The University of Wyoming applied and was chosen as a learn along team in the Collegiate Wind Competition in 2021. The CWC, the Collegiate Wind Competition, was started in 2014 by the U.S. Department of Energy to provide undergraduates an opportunity to build skills and connections to help them find jobs in the wind industry. We decided to take on the project development contest aspect of the competition, mainly because it's easier to follow social distancing COVID guidelines, and we saw it as one of the more difficult aspects for a similar future UW team to tackle. I'd like to talk a little bit about the significance of wind energy today. The United Nations has defined a list of 22 global issues, one of which is climate change. And although they produce a decent amount of solid waste throughout their life cycle, wind farms produce no greenhouse gases in regular operation, which is a big plus. A project like this provides valuable jobs and tax money to the local area. Specifically for this project, the local production tax would go directly to schools in the county and throughout the state. We understand that many people value the existence of land untouched by society, and that varies from place to place. That's not really something that we in our scope have addressed too much, except for trying to stay away from structures. And we also think it's important to acknowledge the aviary species concern, which we will show we have addressed in our design later in the presentation. I'm going to pass it on to Nadia to discuss the project requirements.
Thank you, Garrett. So for our project requirements, we basically have two main components, one of them being our project development contest. This had the highest priority, and then we also wanted to create a student organization, and just compared to the project development contest, this only had like a medium priority. The project development contest consists of two main components, designing a 100 megawatt wind farm, specifically in Western South Dakota, and then also conducting a 20-year cost of energy and cash flow analysis. So as far as the rules we were given, everything was kind of laid out for us in our CWC rules, and we broke it down into two different categories. We have our designing and planning category, and then our financial analysis. For our designing and planning category, that consisted of siting a wind farm in Western South Dakota, creating a preliminary design, risk management plan, and then finalizing our design. As far as our financial analysis goes, there were just a lot of different components that you can see in the table, such as our initial capital costs, net annual energy production, and our financing plan, but everything that we included is shown there. As for the section on the right-hand side with those numbers, that's just basically showing you where you can find these rules specifically in the CWC rules. For our design codes and standards, we use them for our setbacks, environmental issues, transportation constraints, transmission design, permitting requirements, and the turbine technology and safety. On the right-hand side are the specific codes and standards we use for each of those. These are not all of them that we use, but they are the main ones that we did. As for our budget and safety, these really were not a concern with our project as we were not given a budget at all. However, our financial analysis that we did come up with is comparable to current wind projects in development. And then as for our safety, everything that we did was completed virtually, so there weren't any safety concerns there. However, if we were to actually be constructing this, the safety of the wind farm would be contracted out to a company that could better handle the issues, and therefore we wouldn't be too involved in the safety either. I'm now going to pass it off to Donovan.
Thanks, Nadia. Now me and Thomas are going to talk about the initial design. The first step in the design process was to determine a county to build in. We were only allowed to use the western half of the counties in the state of South Dakota because of the competition. And we began by taking all of the available counties and ranking them based on wind class, transmission line access, native endangered species, geography, local tax, and whether or not there were any developed wind farms in the area. Early on, we identified a whooping crane migration corridor, shown in blue on the map. And so we did try to develop more in the western half in order to mitigate the costs associated with that. We eventually settled on Lawrence County, shown in red. One of the reasons we chose Lawrence County was because it had a lot of transmission lines in the area. It had a lower local tax rate, and it was a lot flatter than some of the other counties. So that would help us reduce the inflow angles at our specific turbine site. But once we had the county, well, we moved on to where in that county to actually develop a wind turbine farm. Originally, we started to look at designing it just north of St. Ange, in the middle of the map right there. However, there were a lot of obstructions or developed structures in the area, and so there just wasn't space for us. So then naturally, we tried to develop where the higher wind speeds were in the Black Hills National Forest due to the elevation. However, leasing this land from the federal government is typically very difficult or unheard of. And so even if we designed a plant there, it would probably be unviable. So then we moved into the northeastern quadrant, and you can see the little dots there. That's our actual wind farm layout. And what's really cool about this location is there were no structures and really no people there. And it was just north of the intersection of two high transmission lines. And now I'm going to pass it off to Thomas.
Thanks, Donovan. For our turbine selection, we had a few criteria, mostly that it would produce in the range of 3 to 4 megawatts and would be capable of handling the high speed winds in Lawrence County. We ended up settling on the Vestas 4 megawatt platform, mostly for its distance from South Dakota with Vestas's manufacturing plant in Colorado. The Vestas 4 megawatt platform can output anywhere from 3.3 to 4.2 megawatts of power. And we selected the 117 meter diameter rotor for the local wind speed conditions. This allowed us to maximize the nameplate capacity with a minimum number of turbines. I'm going to go ahead and pass it off to Brighton.
Thank you. Donovan and I will now discuss the site design. So to site a 100 megawatt wind farm, we had to apply a pretty complex fluid dynamic model. We also had to apply concepts from thermodynamics, mechanics, circuit, and machine design that we covered in our undergraduate studies. To aid us in generating this model, we used a software called Continuum Wind Energy. We chose this software because it's open source, making it easier for the teammates to download onto their personal computers when working remotely. It can also complete all the computations required by the Collegiate Wind competition. We use this software to analyze the elevation and roughness data, generate the wind flow model, and then we use this wind flow model to optimize the turbine layout and estimate annual energy production for the site. So to make sure we had a valid model, we wanted quality input. So we started very early. We were attending Collegiate Wind competition information sessions, consulting documentation provided with the software itself, as well as doing some independent research. We finally decided on the United States Geological Survey as our source of GIS information. We used their digital elevation product as well as their 2016 land cover product. For wind speed data, we used the National Renewable Energy Laboratory's wind toolkit. We used their land-based wind speeds at 100 meters. And then for turbine specifications, we got that from the manufacturer's website, as well as we had to model the power curve in the system advisor model because it's not readily available. With all these inputs, we were able to generate the wind flow model, and then we were able to optimize the turbine layout by analyzing the up and downwind exposure, as well as trying to minimize our wake loss. We also ran iterations for both the 3 megawatt and 4 megawatt variations, and then consulted with the financial model to see which was most feasible for our site. After that, we were able to analyze our losses and the annual energy production for the site. I'll now pass it on to Donovan.
Yeah, so some of the problems we encountered with Continuum was that it was an industry-specific software package. And so that meant you had to have intricate knowledge of fluid dynamics in order to run the simulations or to actually understand the results it gave you. But we overcame that. And then we also ran into problems with long run times. Trying to determine the wind speed across 500,000 acres took a little over a week. However, we did reduce the time it took significantly as we narrowed down our site. We did also have some difficulties acquiring data, but that just meant we had to go to specific organizations associated with that data. And I'm now going to pass it back to Brighton.
Thank you. So after overcoming some of these problems and narrowing down the site as we previously discussed, we have this final site as depicted on the left. You'll note that this is very close to our high transmission power line from data that we got from Basin Electric. We're within 1.5 miles to where we can tie in and build a substation. We also optimize the orientation using the continuum wind flow model. As you can see how it's slightly skewed. Using our optimized turbine layout, we are actually able to make a collector system, minimizing the transmission distance and minimizing our transmission losses. With the site narrowed down, we were able to update our continuum parameters. On the top right over here, you can see our elevation map, and you can see that the terrain is much more mild than that of the Black Hills National Forest located to the southwest down there in the red and the yellow. The average elevation for the site was 995 meters with a standard deviation of 27 meters over 3,200 acres. From the image on the bottom right, you can see the orange represents the grasslands and the yellow represents the evergreen forests. The model uses the North American land cover key to analyze land cover. So we did analyze the forest to make sure it wasn't a dense forest, and it's not. The trees are just spaced sporadically. After that, we generated the wind flow model for the site. We came to an uncertainty of 0.39%, which we'll discuss a little bit later in the validation efforts. This resulted in wind speeds of 7.63 meters per second. Assuming a loss model of 9.77% over the site, we were able to find a net capacity factor of 33.4%, resulting in net annual energy production of 292,629 megawatt hours. I'll now pass it on to Jake.
Thanks, Brighton. Anders and I are now going to talk about the financial modeling. So the approaches for the financial modeling, the analysis had to include some engineering economics, some advanced financial modeling, as well as a simplified energy production model, which was simplified relative to the continuum model that we have previously discussed. To model this complex system, we decided to use a software program, and that software program is called the System Advisor Model, also known as SAM. SAM is an open source program that's provided by the National Renewable Energy Laboratories, and it was used to conduct our cost of energy analysis and our cash flow analysis based on by a selected financial model, some financial factors, and the site design, which came directly from our continuum outputs. So the initial critical inputs for SAM were the financial model, and we chose to use a power purchase agreement, PPA, partnership flip with debt. And this included having an investor that supported the project along with us as the developers, and we had to include debt to make the project profitable. The model parameters were the internal rate of return target, which was selected to be about 10% to be competitive with other investing options for large private investments, and the IRR target year, also known as the flip year. And in this figure right here, you can actually see our flip year highlighted in red. And the flip year is really just when we switch from most of the profit going to the investor to it going back to the developers. And now I'm going to talk a little bit about the system costs. And these included our initial capital costs, the operation and maintenance costs, and the construction. And these were calculated using hand calculations as well as the land boss model provided by NREL. Then these values were validated against scaled published values from the Choke Tree Sierra Madre project, which you can see over here in this table on the right. And they were scaled to be on a per kilowatt basis, so we could adjust them to our project. And now I'm going to pass it off to Anders.
Thanks, Jake. While we were constructing this financial model, we did have a few challenges with SAM. Most of that came from the complexity of the terms and financial models used. As mechanical engineers, we don't really have a whole lot of background knowledge in that area, so there's a bit of a steep learning curve. There's also just a large number of these terms that we had to become familiar with, and then we had a few minor issues with computers thinking that SAM was a malware program, but other than that, it went relatively smoothly. And then for the most important outputs that SAM gives us, the main one is the PPA price. We had a target value on that of about 2 cents per kilowatt hour because that's the cost of coal energy in the area. And then we just tried to iterate the financial parameters, specifically the flip year and the IRR target percentage, to try to lower our PPA price as much as possible to be competitive with coal as well as other renewable energy sources. SAM also gave us net present values for both the investor and the developer, so just the amount of money that each party makes at the end of the 20-year life of the project, and then the net capital cost, which is a summation of construction and equipment costs. Then I'll pass it back to Jake.
Thanks, Anders. So now I'm going to quickly go over our final design results. So in this figure on the left, you can see our final site layout located just outside St. Ange. And it's also oriented to be in line with the wind with our turbine spacing optimized. The turbine model the final turbine model we went with was a Vestas V117 4 megawatt turbine. The nameplate capacity was 100 megawatts. We had 25 turbines total. The net annual energy production was 292,629 megawatt hours. Our net capacity factor was right around 33.4%. Our levelized PPA price was 5.99 cents per kilowatt hour. Our IRR for the developer was 5.09%, and our investor was 11.67%. And then our levelized cost of energy was 6.96 cents per kilowatt hour. And now I'm going to pass it back over to Brighton.
Thank you. Anders and I will now discuss how we validate the design. So to validate the physical model, we first ran a round-robin uncertainty analysis. This worked by omitting one of the sites that we uploaded wind data for and then using the wind flow model to predict the wind speeds at that site and compare the two values. Initially, we were modeling much of western South Dakota, and this led to really large uncertainties as well as large runtimes. As we narrowed our geographic bounds, we were able to minimize both the uncertainty and the runtime, and we finally arrived at a round-robin uncertainty of 0.39%. So now that we know we were pretty accurate within our model, we wanted to see how we compared to other data. We used the National Renewable Energy Laboratory, the Wind Exchange from the Energy Department, as well as the Global Wind Atlas, and they were all in agreement that the class for the area was 4 to 5 winds, as you can see in the figure on the right. That leads wind speeds in the range of 5.5 meters per second to 10 meters per second, and the average wind speed calculated over the site was 7.6 meters per second, which lands right in the middle of this range. To validate our net annual energy production and our capacity factor, we also used comparator data. We compared it to reports of other wind turbines in the Western United States, as well as to other collegiate wind competition reports. We also validated the continuum model against the SAM model. Initially, the SAM model had very basic inputs with a square layout, and the difference between those two models was 1.78%. As we were able to update the SAM model with the continuum outputs, this was minimized. I'll now pass it on to Anders.
Thanks, Brighton. As for the key outputs from SAM, we validated the PPA price against published values for other wind farms, renewable energy sources, as well as coal in the United States. And then we also compared them to values from other CWC reports from prior years. This was the most valuable as they had the same requirements and we're trying to achieve the same thing as our team. And you can see a summary of a selected few of their PPA prices in the table on the right side there. And ours is actually quite low compared to the average of other teams. We also validated the net present values and the capital cost of our project against the other CWC reports as well, because it's one of the easiest ways to get a hold of that information. And with that, I'll hand it off to Thomas.
Thanks, Anders. I'm going to go over some of the conclusions for today. So firstly, our project success based on our requirements, we feel is quite successful. We were able to complete the project development contest, including the 20-year cost of energy and cash flow analysis, and the 100 megawatt wind farm that we designed in South Dakota. However, we didn't do a computational fluid dynamics analysis for each site like we initially intended to. We got rid of that due to time constraints. We also abandoned the student organization due to time constraints, the student organization falling outside of the scope of this class, and issues we ran into with the pandemic. Moving on from that, we do have a couple recommendations that we would like to make to ourselves at the beginning of this project or for future teams competing in the CWC. Firstly, a larger multidisciplinary team would have been nice. The full scope of the CWC was just too great for us to handle. The additional disciplines that would have helped would have been electrical engineering for the design of a wind turbine, and business, finance, or economics majors would have made it easier for us to do the financial analysis. Further, we would have liked to start earlier or at least reduced our scope a lot earlier. It would have allowed us more time to iterate or investigate potential sites. And finally, completing the iterations in order. We kind of went out of order and it made things a little bit more difficult for us than it needed to be. And so we'd like to give a couple thanks to Dr. Solinger, our sponsor, Sarah Buckold, our technical advisor, Dr. Kuhn and Dr. Narton, the professors, the Department of Energy for organizing this contest, Liz Walls, the developer of Continuum, and the judges for today's presentation. Thank you, guys. Do we have any questions?
Thank you. Questions from the judges?
Yeah, this is Joe Wright. Number one, that was a really good presentation. I was impressed. My question is were you able to, I guess, do you have the information available where you could actually look at other established wind farms to see, basically to validate some of your assumptions utilizing the software that you're using?
On the financial side, yes. The Sierra Madre Chokecherry project over in Rawlins has extensive financial records published through the state of Wyoming. And then we were also able to glean a lot of information from like permit applications and such for wind farms in South Dakota. As for Brighton's side of things, I don't know, did you look into that much?
Most of our validation was against like the SAM model as well as the reports they were getting there. There wasn't a lot for just like a 100 megawatt wind farm should put out this much readily available to us.
Sure.
And the companies that make the wind turbines tend to be rather protective of specific information about them. So that was something that we were not able to gain a lot of information on.
And was the idea of the student organization, is that internally developed by this team, or was that something that came as a part of this project?
Yeah, I can address that. So it was developed by this team to try to have a group of students to continue this work after next year, to continue and to fully compete in the CWC next year. But it just didn't really fit with how we were trying to conduct the senior design project.
No, that makes sense. I think it's a great idea, though.
Yeah, I had a question about the when you say the average wind speed and the analysis. Did you do that month by month, or how is that done, or what is your prevailing wind direction and things like that?
So if you want to go to that other side, we used a wind speed, wind direction joint probability distribution and the data is over a year span.
Yes, some quick question here from Xiang. So the first question is also regarding your choice. I think in one of the slides you mentioned based on the average wind speed, you choose the diameter of that rotor blades, like 117 meters. So I'm curious in knowing more about this process. So in that decision process, is the wind speed the only input? Then you have some sort of a tabular information, you check out the diameter, or that process actually considers more other factors?
It's mostly the wind speeds from the manufacturer. They rate each turbine and each rotor diameter with what class wind speeds it can handle. And looking at it, 117 meters was the largest rotor we could get to match our wind speeds. Anything larger wouldn't have been able to handle the average wind speeds at our site.
I see. Yeah, thank you. And also another question is regarding, so basically through this project, you guys are actually going through a entire design workflow, right? Even though this competition is for location chosen to be in that South Dakota, but my question is, if I want to add a comment on if we want to apply the same workflow for a wind turbine, a wind farm design here in Wyoming, right? What aspects or what things you need to change?
Most of the site-specific information were like the local ordinances and taxes, I believe. I don't know if somebody else probably has slightly more to say than I do, but yeah, it's mostly just like zoning ordinances and tax rates in the area.
I would also, I would add that definitely environmental factors. We don't have, I mean, the whooping crane population is different here, obviously. Also, there's been a lot of talk recently, specifically in Wyoming, about actual herd species that are moving through the area and how wind farms affect that. And so I think that from an environmental factor, from that aspect, it would definitely change a lot of our site selection detail as to exactly where we decided on putting our project, our wind farm.
Yeah, to piggyback on that, the Chokecherry Sierra Madre project did have they had to work around this area that was designated as a sagebrush protection area or habitat area. So just with the environmental stuff would change.
I see. Great, thank you.
Time for one last quick question from the judges.
I have one. You said there were two high voltage lines for potential interconnection. Were you able to determine what the voltage of those lines were, and did that have any impact on your analysis to improve cost to interconnect with one over the other?
Yeah, the line just to the west of us was a 69 kilovolt line. It runs directly nearby our wind layout. However, we can't actually connect into it because it doesn't have the throughput to actually handle a project of our size. So that's why we went further south to the interconnection spot where there's a 230 kilovolt line that would actually allow us to tie in.
Yeah, and we have a visual for that, if you wouldn't mind pulling it up on slide 55, where we have drawn out a red line that just connects our wind farm down to the 230 kilovolt down there. And that 230 runs, I think it runs across the whole state pretty much almost completely from east to west. But that 69 kilovolt does not already have a substation there. So we would actually have to build a substation at that new location, but we kind of piggybacked along with the line that was currently there to try to maintain some sort of a energy pathway, should we say, not undisturbed areas as opposed to transmission lines.
And the only other thing I would add for that is it did reduce our cost from the building the substation was actually cheaper than transmitting to the nearest substation, which was actually located outside of Spearfish, South Dakota.
Yeah, it was about 10 miles away. The transmission lines are expensive.
Mm-hmm. So how far is it from the southernmost turbine to that interconnection point? Just help me scale wise.
I believe it was 1.39 or so.
Yeah, okay.
It wasn't too incredibly far. So
cool. Nice work, guys.
Thank you.